Assalamualaikum and good day everyone. So as for today, we are going to continue on the design example for the RC beam. Right. So as what we have already discussed before in the previous video, we have already looked into the loading analysis as well as the loading transfers. Right. So we have already we have already do the analysis, whereas we have already transferred the loads from the slabs to the beam, and then we also have draw the bending moment and also shear force diagram, right? So this is the figure of the critical sections that we are going to design, right? So basically we are going to look one by one on the design of the main reinforcements as well as for the design of the shear reinforcements. Right, so we will start with the first part, which is the design of the bending reinforcements. So since we are designing for symmetrical beams, so three critical locations is to be designed, which is the middle end of end span, no, the middle of end span. Then we have B, the middle of interior span, and also C, which is the interior support. Right, so we can see here, those A, B, C, is actually designated in the bending moment diagram. Right, so these are the values of the bending moments that we will be referring to. Okay, so for the design, as usual, we are going to start with the calculation of the effective depth. Right, so this is very important, because in the design of a beam, we will be using the effective depth instead of the overall depth of the section. So earlier, we have already assumed that the bar diameter is 20 mm, and also the link diameter is 10 mm. And with regards to the cover, nominal cover, we have already determined, and the nominal cover, considering the condition, the durability, bonding, and also the fire resistance, the value is 35 mm. So therefore, in consideration of all those, we can calculate the value D, which is 445 millimeters. Right, so this is for our beam. Right, so we are going to start with the first location, which is at the middle of end span. So as for this part, it can be designed as flange or rectangular section, and this actually depends on the location of our beam. So as for our case, so here we have a middle of end span, which is located here. And if we refer back to the layout of our beam that we are designing, which is in green, right? So we know that we have this beam is connected to the slab. So it is at the exterior part of our building, right? Which is within the perimeter of our structure. So we can see here, that it is supporting slab only in one direction, only in one side, right? So it means that the beam that we will be designing will be an L section. Whereas if we are drawing the cut section of our beam, right? So you can see here, that if we do a cut section here, then you are going to see that actually we are going to have our beam that looks like this, right? So this is the beam, and this is the connected slab, right? So we know here, that the design, that we have here is the design of a flange section, and the flange section, that we will be designing is an L section, right? Okay, so we have to know, you have to know this, right? So it is very important, because we need to use the correct method, and also determine the correct B that we are going to use in the design process. Okay, right. So since we are designing for a flange L section, so therefore, we are going to have here okay, we are going to have to calculate for the effective width of flange, right? Okay, so as what I have already shown you earlier, right? Okay, so we have already go through one example on the effective width of flange, okay, right? Okay, so we are going to use that calculations as well in our design, right? Okay, so we are going to start with that, right? So for the end span, okay, so since this is a continuous beam, so we need to calculate the L naught value first, right? Okay, so we have this equation L naught, okay, in the equation for the effective width, okay? Right, so we have 0.85 times with 7.2, right? So here we have 6120 millimeters. Then calculate the effective width of flange. So we are going to substitute, okay, the values into the calculation, right? Okay, so we know that in the calculation for the effective width of flange, okay, we need to consider the cross-sectional view as well, right? And since we are designing for an L section, right, so we are going to only have BEFF one, right? Only from one side, right? So you can just substitute, okay, all the values that is required from the our layout, right? Okay, and we are going to get, okay, the value of BEFF equals to 1142, right? Okay, so 1142 mm, okay, and we are going to compare with B, right? So B is the limiting value, right? Okay, so therefore we can use our value that we have already calculated. Okay, and since in the design, okay, usually we are going to round up the value, right? So therefore, we are going to use the B value as 1140 mm. Okay, right. So that is for the BF value, right? Okay, so the next part, okay, in the design, okay, is that we are going to calculate the values of AS minimum and AS maximum, right? So AS maximum and AS minimum are the limiting values of our area of reinforcement. So you have to calculate this first. Okay, so AS minimum, okay, is equals to 0.26 FCTM BD over FYK, then multiply with 0.0013 BD, right? Okay, so these are the standard equations, okay, that we are using for the design of a beam, okay, as well as for the design of a slab, right? Okay, so we are using the same thing, okay, only that the same equation, only the difference is that is the value of the B value, right? So for slabs, usually we are using the um, value one meters, okay, right? Okay, but as for beams, okay, then we will be using our own beam. Okay, so and please bear in mind, okay, that in the calculation of AS minimum, okay, the B value that we are considering here is BW, right? Okay, so we are not going to consider BF here, right? Okay, so it is not the flange section. So we will be only using the BEFF value only for the calculation of K, but not in the calculation of AS minimum. Right, so here we will be using BW, right? So similarly for the calculation of AS maximum, right? So AS maximum also will be using BW times with H, right? Okay, so this is another thing that you have to remember, that in the AS maximum calculation, okay, we will be multiplying the value with H, okay, as the cross-sectional area of our concrete, right? So instead of considering D in the calculation. Okay, so those are the calculations for AS minimum and AS maximum. Okay, so next, since we are designing for a flange section, okay, so therefore we are going to calculate MF, right? Okay, so what is the reason of calculating this MF? It is to determine the location of the neutral axis, okay, whether it lies in flange or it lies below flange. Okay, so if it lies in flange, means that we are going to design the beam, okay, using the rectangular section equations. Okay, but still the beam is still a flange section, only that the equations that we apply, okay, can be using the equations for a rectangular section. Okay, right, so we are going to substitute, okay, the values that we have already obtained earlier, right, into this equation MF, right? So we have 0.567 FCK BHF, right? Okay, so please bear in mind that here this B value must be the B for flange, right? Okay, so it is not the B for web, right? Okay, so you are going to substitute this value of 1140 calculated earlier. Then proceed with the calculation with D and also HF, right? So this HF is the slab thickness, right? So earlier in the calculation, okay, before we transfer the loads from the slab to the beam, okay, we have already done the estimation of the slab thickness, right? So therefore, that would be the slab thickness that is to be considered in the beam design. Okay, right. So it proceeds. Okay, so for the design process, okay, actually we are going to have a continuity in the calculation, right? So we are going to calculate one after another, and you have to refer back to what you have already calculated. Okay, so here we have 772 kilonewton meter. So this is the MF value, right? So this MF value is to be compared with the design moment, right? So in order to determine whether the neutral axis lies in flange or below flange, okay, you need to compare this with the design moment that is from the bending moment diagram, right? So if we refer back, okay, to the bending moment diagram, okay, so since we are designing for this location, right, so we have the moment of 154.15. Okay, so we are comparing here. So 154.15 kilonewton meter is the design moment. Okay, and the MF value is 772 kilonewton meter. Right. Okay, so what we have here is that our design moment is lesser than MF. So therefore, okay, we know that the compressive stress block lies in flange. Right. So the neutral axis lies in flange. Therefore, this beam can be designed as a rectangular section. Right. Okay. So when we can design this as a rectangular section, so straightforward, you can refer to your design appendix. Okay, and you can use the equations for a rectangular section. Okay. Right. So for a rectangular section, we are going to use K equals to M over B D squared FCK. So even though we are using this equation, okay, however, there is some difference here. Okay, whereas the B value here must be BF. Right. Okay, so please bear in mind, okay, that you will not be using BW, right? Okay, since you are designing for a flange section as a rectangular section. Okay, right? So this value here is 1140. Okay, and it is not 200 mm. Okay, but then all the other values, okay, will be using the same values. Okay, so here we have K equals to 0.027. Okay, so compare with K balance, which is 0.167, right? So therefore, compression reinforcement is not required. Then calculate Z, compare with 0.95D, right? So the value that we have here is 0.97, okay, which is larger than 0.95D. Okay, however, the limiting value given in the British standards is only 0.95, right? Okay, so since the value is larger than that, right? So therefore, you are going to use, okay, the limiting value. Okay, so proceed with the calculation. So we have AS required. Okay, so substitute 0.95D into the next equation, right? So we have 838 millimeter square. Compare this with AS minimum, right? So the value that you have provided, okay, must be in between AS minimum and AS maximum, right? Okay, so here we have AS minimum is AS minimum, if we refer back to the previous calculation, is 120, right? So what you have is more than AS minimum. Okay, and the value that we have provided. Okay, so as for this, we require 838 millimeter square. So we can propose to provide 3H20, okay, with the AS provided of 942 millimeter square, right? So we can also compare this with AS maximum, okay, whereas we have already calculated the value of maximum area of reinforcement as well. Okay, right. So can install in one single layer, right? Okay, so as for this, we also have to check for the clear spacing, right? So clear bar spacing, okay, is the distance between the bars, right? So later we are going to look into that. Okay, right. Okay, so here, okay, so the calculation is here, right? So assuming that the maximum aggregate size, okay, is 20 mm. right? Okay, because we are dealing with a reinforced concrete structure, okay, whereas we need to have the the concrete, okay, passing through in between the reinforcements. Okay, so therefore, okay, we should have enough space between the reinforcements. Okay, so for example, as for this, okay, what is mentioned here, okay, is with regards to the arrangement of the reinforcement. Okay, whether it is giving us an appropriate clear bar spacing or not, right? Okay, so here, if we arrange this in one layer, okay, of 3H20, okay, then we are going to see, okay, that we are going to have this as the clear bar spacing. Okay, so this is the distance. Okay, so to calculate this, okay, we are going to assume that our maximum aggregate size is 20 mm, okay, which is the standard aggregate size that we usually use in the concrete mix. Okay, so the allowable clear bar spacing, okay, so this CBS is actually clear bar spacing. Okay, so clear bar spacing. Okay, so we are allowed, okay, to have a maximum of 20, okay, which is the maximum aggregates, okay, and also 20 plus 5, right? So that 5 is actually the coefficient, okay, that is given in the or allowance, okay, that is given in the Eurocode, okay, and then we also have 20, right? So 20 is the least value of the reinforcement. Okay, right? The least value of the clear bar spacing. Okay, right? Okay, so when we compare this, okay, so we need to determine which value, okay, is the highest value, right? So as for this, okay, the highest value is 25 mm, right? Okay, so we are going to use this, okay, and compare, okay, with the distance, okay, between our reinforcements. Okay, so how are we going to actually calculate the value, okay, that is for the clear bar spacing? Okay, is that you have to determine this spacing. Sorry. Okay, you need to determine this distance. Okay, whereas as for this, okay, we need to consider the cover, okay, and also you need to consider the diameter lengths, right? Okay, so as for this, okay, so we have the CBS actual, okay, is 27 mm, right? Okay, so therefore the requirement is 25 mm, right? So this is considered as acceptable. Okay, right? So this is one of the things, okay, that you actually have to calculate, right? Okay, so this 27 is actually from the BW, okay, distance minus width, okay, two covers, okay, then minus width, okay, so two covers is for the two sides, okay, then minus with 2 times diameter length, okay, and also minus with 3 times diameter bar. Okay, and from here you are going to get the CBS value or the clear bar spacing, right? So you can try to do the calculation, right? Okay, and also check, okay, with the allowable value, right? Okay, so what we have should be more than the allowable value, right? So it should not be lesser. So if it is lesser, then you have to do adjustment, okay, on the selection of reinforcement, okay, that you are taking, right? So perhaps maybe you can change from 3H20 to 4H20, 4H16, okay, so that you can arrange the reinforcements into layers, right? Okay, so that is also an option, okay, in order to increase the distance, okay, between the bars. Okay, so that is one option. Okay, so what is the result if you design it as a rectangular section, okay, of 200 times with 500? Okay, so you can also do uh, uh, this exercise, right? Okay, in order to find the difference, okay, between designing your beam as a flange section or you are designing your beam as a rectangular section. Okay, right? So that would be the exercise that you can do. Okay, so that is for the first location, okay, which is at the end mid span. Okay, then the second location is location B, okay, which is at the first interior support. Okay, and since for this location, Okay, the bending moment is at the support, okay, which is where usually we have the location of the column, okay, or we have the location of a supporting beam, right? Okay, so therefore at this section, we can only design our beam as a rectangular section, right? Okay, so we cannot design this part as a flange section. Okay, so for this, we are going to repeat, okay, the same equation, okay, which is for the rectangular section. Okay, only that we are going to skip the MF step, right? Okay, so as for this, we have the bending moment, okay, value of 256.45 kilonewton meter. Okay, so substitute into the calculation, and you can see that in this calculation, since we are designing this for a rectangular section, so the B value that we will be using is BW. The B value, okay, that we are using will be BW, okay, instead of BF, right? Okay, so we are going to go into the normal rectangular section. So we have BW times with H. Okay, right. So we have here compression reinforcement is required. Okay, so therefore you are going to calculate for Z balance. Okay, then calculate also for D prime. Right, so D prime is for the location of the effective depth, okay, for the compression reinforcement. Okay, so calculate for D prime as well. Okay, then calculate AS prime required and also AS required, right? So when you have compression reinforcements, so it means that you have to design for both the top and also bottom bar, right? Okay, so AS prime required, okay, we are having um, 543 k millimeter square. Okay, so proposed 3H16. Okay, and also for AS required, okay, we have AS of 1584. Okay, so compare this with AS minimum as well, right? Okay, so we are going to have we are going to use 1584. Right. Okay. So as for the proposed reinforcement, okay, so we can also propose the reinforcement for the AS required, okay, to have the reinforcements in two layers, right? Okay, so two layers, okay, means that we have two different bars, right? So we can also use similar bars, okay, but only the arrangement is different. Okay, right. So here we have AS provided, okay, is 1610. Okay, assuming that the maximum aggregates is 20 mm. Okay, so again we can also calculate the clear bar spacing. Okay, right. So the allowable clear bar spacing again is 25 mm. So when we calculate, okay, for this 2H25 and 2H20, okay, we cannot actually arrange this in one layer, right? Okay, so if I draw this, okay, then actually we cannot arrange this in one layer, okay, because we are going to have four reinforcements. Okay, so please do remember, okay, that the reinforcements in the beam has to be of a symmetrical arrangement, right? So the left and right, okay, needs to have the same reinforcements. Okay, so you cannot bunch 2H25 to the left and then we have another 2H20 to the right. Okay, so it has to be symmetrical. So if you are to put these reinforcements in one layer, okay, it means that you are going to have 2H25 at the sides, okay, and then 2H20 will be at the middle. Okay, however, with the calculation or with the checking, okay, so we know that, okay, the clear bar spacing will be very small, right? Okay, so if it is very small, then it will not allow the aggregates to pass through, right? Okay, so in order to adjust to that, okay, so we need to provide 2H25 and also 2H20 into layers, right? Okay, so therefore, instead of using this arrangement, okay, so we can change it to this layer, right? Okay, so this is the links. Okay, so as for the reinforcements, okay, so usually we are going to put the bigger reinforcement at the bottom, right? So we have 2H25 at the bottom, okay, then plus with 2H20 on top, right? Okay, so we are going to have these two layers of reinforcements. Okay, so with this, okay, you can see the difference here, okay, is that this is the clear bar spacing if you are arranging all the four reinforcements together, right? So the spacing is very small. However, when you change it to two layers, okay, what happens is that the clear bar spacing is increased to a wider area, right? So this will allow the maximum the aggregate to pass through, right? So this is very important, right? So even though you can design and also you can provide the reinforcements as you wish, as long as it is more than it as required. However, your provision needs to also consider the construction process, right? So how the reinforcements will be arranged on site, right? So you as the designer, needs to have this knowledge. So the next part is on location 3, right? So this is the third location, whereas we have the middle of interior span, right? So for the middle of interior span, so again, we will be designing this as a flange section because it is connected to a slab, right, on one side. However, with regards to this, we know that the value of the bending moment is different from the previous calculation for section A, right? Because that is for the end span, but now we are referring to the middle, to the interior span, right? So if we refer to this back, right, so this will be the value of moment that we are going to look into. So as for this, so for location 3, so at middle of interior spans, so it can be designed as flange or rectangular section. So for this location, we are going to design this as an L section again. So end span, L naught is equal to 0.7. So 0.7 times with L, right? So this value will be based on the equation for BEFF, right? So you can refer to your Eurocode. I have already shown you this. So calculate this, and we are going to use BEFF equals to 1,100. For the effective width. So design the main reinforcement. Whereas we have MF equals to 0.567 FCK-BHF. Right. So this is again, since we are designing for a flange section, so we need to determine the location of the neutral axis first. Whether it is in flange or it is below flange, right? So calculate MF, so we have 745, and also MED is 1,163. So when we compare, so we have our MED value is lesser than MF, right? So similarly to the section A just now, right? So the compressive stress block lies in flange. So therefore, we are going to design this as a rectangular section, right? So calculate K, calculate Z, calculate A as required. So we are going to provide here 3H20. Whereas AS maximum, we have to compare back to the value that we have calculated earlier, right? So again, here we have to check for the clear bar spacing, right? So 3H20 is actually similar to the previous one that we have already designed, right? So therefore, we know that it already fulfills the requirement. Right. So that is for the main reinforcement design. So next we move on to the shear reinforcement design. So for the shear reinforcement design, again, this falls under the ultimate limit state, right? So it is similar, right? So the design of the main reinforcement as well as the design of the shear reinforcement. So both falls under the ultimate limit state calculation. Right. So design the shear reinforcement. So the common practice is to carry out design for 3 locations for each span, which is approximately 1/3 of the span. Right. So as what I have already shown you earlier, is with regards to the critical sections. So for the shear force, shear reinforcement design, right? So basically, we are going to look into these 3 locations. For each span. So if we look back to the calculation, right? So for the design of the shear reinforcement, we are going to look into the first span, which is the location 1, near the support, near the first support, with the VED value of 0.45 F, which is 107.05, right? So this is the first location, right? So if we look here, so this is the first location, that we have for our shear reinforcement design, right? So we are going to look into the calculation for this first. So VED is Okay, so VED is equals to 107.05 kilonewton. Okay, so proposed reinforcements for the end span, right? So for this value of the proposed reinforcement, we are going to refer to what we have already designed, right? So we have 3H20 at midspan. Okay, assume no curtailment is made, okay, at the ends. Okay, so therefore we are going to take 100% of the reinforcement. So 100% of the reinforcement is 942 millimeter squared, right? So this is the area for 3H20. Okay, then K is equals to 1 plus with 200 over 445, right? So these are actually the equations, okay, that is calculated to determine the value of VRDC. Okay, and what is VRDC? So VRDC is actually the equation, okay, that we calculate in order to determine whether the shear reinforcement is required or not. Okay, and to do this, we are going to refer to the flowchart, right? Okay, so this is the shear reinforcement design procedure, right? Okay, so we have this in the previous lecture note. Okay, whereas I have already explained to you with regards to the shear reinforcement design procedure, right? Okay, so as what I have already promised, right? Okay, this flowchart is to be used together with the calculation or with the example. Okay, so the first thing that you have to calculate is this value VRDC. Okay, so why do we have to determine this? It is in order to determine whether your section requires shear reinforcement or not, right? So if it does not require shear reinforcement, so therefore we are going to design only for the minimum links, right? So we are going to still provide links for your section, only that we are going to provide only minimum links, right? So we are not going to design for shear reinforcement. So we can see here that this case falls when the shear reinforcement is required when our VED is larger than VRDC, right? Okay, so just now I told you that you need to calculate VRDC, then this value is to be compared with your VED from the shear force diagram. Okay, so here, if the VED value is larger than VRDC, therefore the shear reinforcement is required. Okay, so we go back to the calculation just now, right? Okay, so we have VRDC is equals to 53.83 kilonewton. Right? Okay, so all the calculations, okay, that is for the VRDC has to be made, right? So we can see that for K, okay, the value is limited to 2, right? Okay, so the value should not be more than 2, right? Okay, so if it is more than 2, then you are going to just use the limiting value for the VRDC calculation. Then as for the rho L value, right? Okay, so the limiting value is 0.02, right? Okay, so if your value is larger than that, then you are going to just use the limit. Okay, right. So VED is 107.05 and VRDC is 53.83. Right. Okay, so we know that VRDC is smaller than our VED, so therefore shear reinforcement is required. So if we refer back to the shear reinforcement design procedure, right, so we can see that the flow to our case K is in this direction, okay, whereas shear reinforcement is required, right? Okay, so in order to do this, then we are going to design the shear reinforcement. Okay, so and to design the shear reinforcement, we are going to do another comparison, okay, which is the comparison to the VRD max. Okay, right. So the equation for the VRD max, okay, is this. Right. Okay, so you can find this equation, okay, for this VRDC and also VRD max in your design appendix, right? Okay, so if we refer to your design appendix, okay, then we can see that we have those equations stated in this design appendix. It is supposed to be here. Okay, it is not in the design appendix, right? So you have to refer directly to the Eurocode, okay, for the equations, right? So later I will give you the okay, you have it here. Okay, sorry. Okay, so we have the equation here, okay, which is for the design for shear, right? Okay, so you can refer to your design appendix. So you can see that we have the equation for BRDC and also you have the equation for BRD max, right? So no need to worry, okay, with regards to the equation. So you can just simply use these equations and also substitute, okay, all the values that is required. Okay, right. So if we go back to our example, right? Okay, so here we are going to calculate for VRD max, right? So VRD max at 22 degrees K of theta, right? So substitute all the values and we are going to have here 250.39 kilo Newton. Okay, so compare with our VED. So again, we are comparing with VED, right? So if we look here, okay, so the value that we will be comparing here is VED again, right? Okay, so if we look here, our value of VED is 107.05. Okay, so it means that the concrete strike is safe, right? So therefore, we are going to use theta equals to 22 degrees, right? Okay, so if we go back to the flow chart, okay, so we have our VED, our VRD max is larger than VED, right? So therefore, we are going to go this way. Okay, whereas the answer to that comparison is yes, right? Okay, so therefore we are going to go to the flow on our left, right? Which we are going to design the shear link directly. Okay, right? So we have the equation of ASW over S, okay, larger or equals to VED over 0.78 D FYK cotangent theta. Right, and just now we have already calculated, okay, the VRD max value. So we know that that cotangent theta, that tangent theta of 22 degrees is applicable, right? Okay, so the theta value that we are going to substitute into this equation will be 22 degrees. Okay, right? So we are going to calculate that equation, right? And we are going to have here 0.25 millimeter squared per meter, right? Okay, so this is the value that we obtain, okay, from the equation, okay, whereas we have ASW over S, okay, right? Okay, and then we are going to propose, okay, H8 200, okay, which with the ASW over S of equals to 0.5 millimeter squared per meter, right? Refer to this table, right? Okay, so you can refer back to your design appendix, okay, and you can find that you have the table of reinforcement, okay, for the table for shear reinforcement. I have to scroll down. Okay, right? So we have ASW over S for varying stirrup diameter and spacing, right? Okay, so here, okay, we are going to compare, okay, the value that we obtained for ASW over S required. So as just now, okay, we have 0.25. Okay, so 0.25. Okay, so when we provide the length, okay, so you can actually determine, okay, based on the ASW over S ratio. Okay, so as for our selection, okay, so we have chosen to use 0.5. Right, okay, so therefore we are going to use H8 200 center to center. Okay, right, so if we refer back to the example, right, okay, so that is the reinforcement that we are providing, which is this. Okay, so we have H8 200. Okay, so that is one method of determining the shear reinforcement. Okay, whereas you can use the table. Okay, however, if the table is not available, okay, what you can do is actually to calculate separately. Okay, so what you have here in this calculation, okay, is that we have ASW over S. Okay, right? So ASW over S is actually the ratio, okay, between the area of the links. Okay, so this is the cross-sectional area of the links. Okay, and S is the spacing between the links. Okay, right. Okay, so if you are not given the value of the table, okay, so what you can do is that you can calculate this manually. Right, okay, so the ASW over S required is 0.25. Okay, so this is the required area of reinforcement, and we know that the area of link, okay, can be calculated manually. All right, okay, so this ASW can actually be calculated by two legs, the area of two legs of diameter link. Okay, so and how are we going to calculate this? So we have to make assumption on the diameter link that we are going to use. So for example, let's say if we are using this, okay, so try H8. Okay, so it means that the diameter of our length is 8 millimeters diameter. So we can actually calculate the bar diameter. Alright, so for one diameter, it is 8 squared over 4. Okay, pi 8 squared over 4. So this is the area of one leg of the length. Okay, however, the other leg, okay, has to also be calculated. Okay, so why I calculate the other leg? Okay, it is due to this. In a beam, okay, the arrangement of links looks like this, right? Okay, whereas it will be covering the whole part of our beam. Okay, and if we do a cross section across this link, so we can see that we have two cross sections. Okay, so two area of links. So we are going to have two legs of the links. Okay, so that is why we have to multiply this by 2. Okay, so here if we calculate, okay, we are going to get, okay, a moment please. I need to calculate this first. I cannot find my calculator. Okay, a moment please. Okay, right. So we have pi, okay, multiply with 8 square, okay, divided by 4, right? Okay, so 1 bar, okay, the area of 1 bar is 50, okay, then multiply this with 2, right? So it is approximately 101 millimeter square, right? Okay, so this is for H8, right, which is considering the two legs of the reinforcement. Okay, and how are we going to estimate, okay, the spacing, okay, between the reinforcements is by calculating this, right? So we have ASW over S required as this. So ASW is equals to 101. So we are going to substitute this into this equation. So therefore we have 101, okay, divided by 0.25. Okay, and we are going to get the spacing. Okay, so therefore here we are going to have 101 divided by 0.25. Okay, so the value that we are going to get here, okay, is 400. Okay, approximately 400 mm. Okay, so this will be the spacing, right? Okay, so this is the spacing that we can actually provide, okay, if we have a 0.25 ratio, okay, of the spacing required, right? So we can actually provide H8, okay, so we can actually provide H8 400, okay. So this is also sufficient, okay, in order to provide, okay, the reinforcement for that particular area, right? Okay, so this is actually almost similar to what we have in the table, right? Okay, which you can see here. Okay, the table gives us only up to the spacing of 300. Okay, because in on site, okay, usually we are going to go for a standard of 300 millimeter center to center spacing, right? So we do not want the spacing to be too big, right? Okay, so usually we are limiting this to 300, and you can see that even at 300 millimeter center to center spacing, okay, the value is still 0.335, which is still larger than 0.25. Right, okay, so we can you can either use, okay, the manual calculation, okay, to determine the reinforcement, or you can also use this table in order to determine the spacing and also reinforcement that is suitable for your section. Okay, right, so that is one, okay, which is for the calculation, okay, of the shear reinforcement design. Right, okay, so that is for the one location, okay, which as for the area of reinforcement, okay, you need to compare as well for with the S maximum. Okay, so you can see here for the S maximum, okay, so it has to be a minimum of 0.75 D, okay, which is equals to 333.75 mm, right? So if I'm not mistaken, is supposed to be in your in your design appendix. Wait, I will check. Okay, right. So if we look here, okay, in the calculation for shear, okay, additional minimum shear length. Okay, so the spacing is not given here, right? So actually the spacing has to be referred to from the Eurocode, right? Okay, so basically, okay, this is the maximum spacing, okay, that we have. Okay, so S maximum, okay, is equals to be the minimum of 0.75 D, okay, or the minimum dimension and compare with the minimum dimension of our beam, right? Okay, so this is actually the value of BW. Okay, right? So we are going to compare. So the lesser value here is 200 millimeters. So we are going to compare with what we have already provided. So as for this example, we have already provided 200. Okay, so therefore, okay, we consider that the one that we have provided is suitable. Okay, however, okay, if you have already provided this, okay, which is 400, so 400 is more than the S maximum. So S maximum is the maximum spacing between the links, right? Okay, so it has to be limited to a certain value. So as for this, okay, if you are calculating this manually, so this is more than a S maximum. All right, so basically we cannot use directly the value 400, but we have to change it, change this, okay, to 200 mm, okay, which is the maximum value, right? So therefore, again, we are going to change this to H8 200, right? So those are the requirements, okay, that we have to fulfill, regardless of whether you are using the table or you are using your manual calculation. Okay. Right. So next is the first pen, okay, which is location 2. So this is for the near the first interior support, right? So again, we are going to repeat the same steps, okay, only that now we are changing the location, okay, whereas the VED value will also change, right? Okay, so shear reinforcement is required as well, right? Then we provide the reinforcement and check for S maximum. Okay, then for the location near the first interior support, okay, only the value is different, okay, but the steps are still the same, right? So calculate, okay, and then, okay, so the last one, okay, will be the checking, okay, for the S maximum, okay. So again, we are going to do the checking as well, okay, right? So those are the steps, okay, that we actually wanted to uh, do in view of the shear reinforcement design. Right, so continue shear design for other critical locations. Okay, for example, span 1, location 3, internal span, location 2, 3. Okay, so you can try to do this. Okay, for your own exercise. Right. Okay, so we actually have to calculate for each and every locations. Okay, because we actually wanted to know, okay, the reinforcement that is required for that particular location. Okay, right. Okay, so with that, we end our design on in the ULS design limit, right? Okay, then for the next video, okay, we are going to have the check for deflection. Okay, so with that, thank you very much, everyone. Assalamualaikum.